this agenda for today. So let's briefly look what's in the pipeline. So as the first thing, we will cover what Qt4MCU's package contains, and that means we will see what exactly is installed together with Qt4MCU's product. What things can be interesting for you if it goes about the files on the file system, and how to understand the folder structure for those. Then we will see how to build and run application from command line for both for the desktop and for the Renesas board. After we build our first app, there will be a time for getting through the CMake APIs that are a default way for building the projects with Qt4MCUs. We will see what is specific to Qt4MCUs and what things are used just from the pure CMake. You'll understand how the Qt4MCUs application build process works, how assets are converted, how fonts are connected to the Qt4MCUs application, and how all of those things are combined together to the binary. So you will have the more like the overview on what you can expect and how the Qt4MCUs is built and how it works. If it goes about building it, but it's also useful if it goes about understanding how in overall how the Qt4MCUs is built and how the concept works. After those 4 steps, we'll have short coffee break, and after the break, we will see how to configure Qt Creator, which is a recommended IDE for developing applications with Qt4MCUs. And once we will have Qt Creator configured, I will do some live coding for you to start developing our training application, which will be the more complex than the first one from the command line. And after the first live coding session, when we will have some skeleton of our application, there will be a time for taking a lunch break and getting some rest. And after we will be back from the lunch, I will cover asset management topic, which is to understand exactly what our tools during the compilation process are doing for your assets, and how you can manage those, how you can control how they are stored, and in which format they are stored, and what that means for your application. And of course, this will be followed by another live coding session, which will demonstrate how to use those things that we have just learned in the real life, in the real example. This is for the first day, so for today. And shortly about tomorrow, we'll see what is different between Big Qt and Qt4MCUs, and why you could use one or not another. You will learn how to style the controls, how to provide different look for your buttons, and so on. Another short coffee break, and then we will get back to see how to translate your application to different languages. Another lunch break, the bigger than the previous coffee break, and after it, we will see how to integrate your application and your QML code, which defines the UI, together with C++ logic that can be anything. What is your backend, for example? This could be communication with other device components that you possibly would like to interact with. But this part of the training will show you how to trigger some actions, how to connect some data from the C++, the pure C++, to QML code, which is just for defining the UI. All right, so let's get through software requirements. And Microsoft Windows 10 is the only supported operating system right now. Linux support will be introduced really shortly in the 1.9 release. So there will be another operating system to work on, and the macOS support is of course planned, but we don't know right now when release date will be for it. but just to make sure that you know, and if you're going to use macOS to develop the Qt for MCUs application, it will be possible in the future, but as I said, we don't know exact date for now. Well, shortly, Qt for MCUs 1.8 for desktop is needed for this training. And in general, it comes with requirement for Qt Creator 4.15. You, of course, will need to have a CMake version, a CMake tool with 3.15 version or higher. And you will need MSVC compiler to build your app on for the desktop. And let me briefly go through the setups, so we will make sure that we are on the same page with those. And if you will have any problems, you can then refer to those things I will be doing to set up your environment if you have still some problems with it. So let me open Qt installer for you. Just a second, okay. So here it is, okay. All right, so just go through the login page. Okay, add or remove components should be selected. It will take a while to retrieve all the metadata that is needed for sure. All right, so first thing, please make sure that you have the latest releases selected on the left side. Let's go to, not this one, let's go to Qt, and just to make sure I have installed the Qt, but you don't need those. I have those for different purposes. Qt for MCUs comes with the parts of it that are needed, so you do not have to install the whole big Qt product. And let's go to developer and designer tools. Qt Creator is installed by default, but you can still need CMake, which is below, so make sure that you have the CMake selected, and we will use Ninja on this training, so please select the Ninja if you are going to follow my live coding sessions to have the tools installed as well. Let's collapse the big Qt, and let's go to Qt for MCUs and expand Qt for MCUs 1.8, and let's review what's there. So there are the boards that you can install, and the support for the hardware that you can install on your device. On this training, we will use a desktop MSVC, and of course, we will use a Renesas board, and in my case, it will be Renesas RA6M3G, and that's well expected board for this training. If you are going to follow this session with the RH850, for example, it could be a bit problematic as our application will need a touch. So this board should be the one that we are working together. But if you're going to develop the application together with me during the live coding sessions, you will still be able to follow it with compiling it for a desktop, and that shouldn't be any problem as well. So just to sum up the things for Qt for MCUs 1.8 desktop and the Renesas EK-RA6M3G, or just a desktop if you are going to use only desktop with me. Let's collapse. And the third-party tools to compile our application to the target board, we will need ARM-GCC toolchain. So please select that one. Of course, we will need well, only this, I think. Okay, right. So great, it's enough. Perfect. Well, If you are going to install anything more and you selected something that you have not installed before, you will probably need to click next. I have all those things, so I will just click cancel. Yes, I would like to close. And right now, let's focus on the MSVC compiler. This one is also a thing that I would like to show you how to install. So I just opened the Visual Studio installer and let it do something before it will start. Okay, my Visual Studio installer just decided to update itself, so we'll still need to wait a bit. It's still doing this. Just to remind you, if you have any questions, please feel free to use the chat and the Q&A section to ask the questions you have. I will try to answer those directly during the training. Perfect. So if you are going to install MSVC compiler, so we will probably then need this one. You will need to select one of the Visual Studio versions. It could be Visual Studio Community 2019, or even it could be a Visual Studio 2017 for Express for desktop. It could be also a professional one. Let's use the Visual Studio 2017 for Desktop Express as an example. I'm just clicking the modify there, and then individual components, and let's search for MSVC. All right, it does not work for some reason. Let's try once more. Okay, it's not there. So let's verify the for the professional. Something has broken during the update for the installer, I think. All right, individual components and MSVC. And let's find the proper version of it. Okay, so MSVC v142 is the one that we are going to use in this training. So just make sure that you have this version of the MSVC compiler for the architecture x64, x86 selected. All right, and the other thing, it's the Windows 10 SDK. So just let's type Windows 10 in the search bar, and then there is Windows 10 SDK. So just please select that one, and that will be enough if it goes about MSVC compiler. While in the future, we're planning to provide MinWG support for compiling our desktop version with other compiler for the Windows as well. And well, maybe the last thing right now, it could be worth mentioning that our Qt for MCUs documentation is available online. And here's the example of it. So doc.qt.io/Qt for MCUs. And here's the all documentation that is for 1.8. And there is a question, can we get the video record after the training? Sure, of course. And there will be the video available for you. But not today. It will be available for you probably 2 days after tomorrow's training. So you will receive the all recording for 2 days, but just after the whole training. And well, this is how the Zoom works. So hopefully it won't be too late for you. All right. So this is documentation. And that's it if it goes about software requirements. Right now, let's look what's installed together with Qt for MCUs installation. And before getting into directory and the folder structure, I will just explain you in overall what you are receiving together with your for instance installation. So the first and probably one of the most important things in Qt for MCUs is quick ultralight graphics runtime. What means this is the engine of our Qt for MCUs. It's a purely new part of Qt family, and that is written completely from scratch for Qt for MCUs. It shares some concept with Big Qt, but in general, it's a new thing. It's written just for microcontrollers to be optimal and fast. And this is a heart of our Qt for MCUs ecosystem that works across different platforms. And this is the common part of the whole framework. You will receive Qt Quick Controls library, which is a subset of Qt Quick Controls 2.0 that you can probably know from the Big Qt. This comes, of course, with the default styles for the controls and with the mechanics to style the buttons, sliders, and so on. So you will be able to implement your own look for your controls and still receive the skeletons for most commonly used controls in the applications. You will receive platform adaptation for the boards you have paid for. So platform adaptation is something that is connecting to quick ultralight graphics runtime. And once quick ultralight graphics runtime is requesting some blending, some drawing of the pixels on the screen or assets and so on, then the platform adaptation is responsible for passing those requests to hardware. So if your board has some GPU, for example, platform adaptation is responsible for passing all of the rendering to the GPU and to draw as efficiently as it's possible on the particular boards. And of course, this could come with bare metal implementation. And as a reference, we have also FreeRTOS reference implementation for operating systems for the microcontrollers. You will receive development tools, so Qt Creator and the Linguist tool for localization. We'll cover the Linguist tool and Qt Creator as well during the training. You will receive offline documentation files and examples with source code to go through all features and see how they work. And right now the folder structure. So let me just quickly open that one. All right. So just a second. All right. So this is my Qt installation directory. I'm on the C drive and then Qt. And let's review the tools that we have installed on the software requirements step. So the tools important for us today are the CMake, of course, which contains the binaries, precompiled binaries for the CMake. Sorry. There is a Ninja tool, which will be our generator for the CMake targets. And of course, there is a Qt Creator, which will be used by us on this training to develop our demo application for this training. And of course, there is a directory Qt MCUs, which holds all additional things that are related just to Qt MCUs, Qt for MCUs, like for example the compiler for ARM, and there are some vendor-specific things if there are any needed. All right. This is about tools, and let's get back to the root Qt installation directory. And let's focus on Qt for MCUs one. So Qt MCUs in the root, so drive C, Qt MCUs. Then there is always a version of your installation. And let's review what's there. So the first bin directory contains all of the tools that are needed during the compilation process, for example, to generate glyphs for fonts, to convert assets, so images, to the formats that are known to Qt for MCUs. There are also some libraries from the big Qt that are needed to run your app on desktop. So if you are going to use our desktop backend to verify your UI or changes to your application on the desktop without uploading that application each time after you're making changes to the device, then you can use those libraries to run your app directly on your device that you're using to develop your product. All right, compatibility directory contains some QML files that are needed by our tools, for example, Qt Creator or Qt Design Studio to still be compatible with the big Qts, as Qt for MCUs contains some QML types that are exclusive only to Qt for MCUs, and this compatibility module is providing the alternative implementation using other QML components that are available in the big Qt to still be compatible with Qt for MCUs. Demo images, as the name indicates, contains precompiled images for our demo applications and for both bare metal and the reference FreeRTOS. Let's focus on the one of those. And for all boards you have installed during the installation process, you will have all available demos. And for example, let's search for the Renesas board. So here you can find the watch demo example, which can be directly flashed on the target board, and you can then review how it works and how it looks on particular device. Demos contains sources for those precompiled demos from the previous directory. Docs, of course, contains the documentation and for example, platform porting guide, as well as there is a document that explains how to provide your own platform backend if you, for some reason, would like to implement platform adaptation for yourself and by yourself. Examples, of course, contains examples, and this is rather a simple thing. Okay, there is a question. What exactly is compatibility folder? Well, so as I said, compatibility folder contains some QML implementation based on the big Qt to cover some types that are exclusive for Qt for MCUs. So just by explaining that with an example. So if you have your Qt for MCUs application and you're going to open the project for it in, for example, Qt Design Studio, you can use this module to still be compatible with the big Qt. So if for some reason someone will decide to compile your application with a big Qt, and then those things from the compatibility folder provides alternative implementation for the big Qt for the types that are exclusive for Qt for MCUs. So by using this compatibility module, you can still keep compatibility for the Qt for MCUs specific things with the big Qt. Basically, that contains implementation for those types that are not available in the QML of the big Qt. Hopefully, I answered the question and the thing that was problematic for you. Just let me know if there are any questions still. Well, so let's get back to getting through the directories. Well, I stopped on the examples. So, well, in the examples, you have the source code for examples, of course, and these are the examples of some particular features that you can use in Qt for MCUs. The include directory, of course, contains some headers needed for compilation. Kits contains the configuration files for Qt Creator, and those are to define compiler, to define the SDK directories and so on for the boards you have installed. So Qt Creator tool is using those kits to to create default targets to compile your apps through the Qt Creator tool. Lib directory contains precompiled libraries with Qt Frames use and parts of it. So for example, let's find something for Renesas board we are using on this training. There was RH50, but oh well, yeah. So not this one, this one. For example, here you have the PNG decoder library for the RA6M3G for the bare metal, compiled with the ARM GCC. And if you are going to look further, you have the null library for it. So it provides just an empty implementation if you're not going to use PNG decoding. And so on, so on. There is also a platform library, there is controls library, and all of the parts that are used in Qt Frames use are located in precompiled binaries there. Of course, if you are going to buy the whole ultimate product, you will receive the sources for the whole Qt Frames use. So there is also a way to compile it by yourself, not just by using the libraries, but by default, it comes with precompiled libraries that are completely enough to start developing your things. The platform contains some platform-specific configurations for those platform interfaces, those platform parts, the implementation for handling the rendering on the GPU and so on. Some CMake configurations with the flags are located directly in the sorry, this is for the NXP, for the Renesas. This contains all the CMake configurations. This contains the whole platform engine for each board you have installed, and it's still possible to compile the platform library by yourself to make some changes. For example, if you are going to change the screen, you will just have to modify some parts of those to use different screen, and that will be completely enough. Well, plugins are plugins for the Qt Creator and for Qt Design Studio. So if you will need some support for Qt Frames use in Qt Creator, and Qt Creator by default will use this directory to search for the plugins, and then it will be installed on your device and in your tool. Well, it's just to hold those things there. And the source contains some well, application level reference implementations for some, generally speaking, usual cases. So for example, default main implementations that can be used to speed up your project start, some configuration for the FreeRTOS, some mains for the bare metal and the FreeRTOS as well, some third-party things like the fonts or some monotype parts. And well, this is shortly about what is installed in Qt Frames use. And right now, I think we can go to the next slide. And I mentioned that a few times that there is something like desktop backend, and this is based on the Big Qt. So this is kind of a platform which implements the host backend to render your Qt Frames use application directly on the host device. And this is especially needed to, well, maybe not needed, but especially useful to verify your application on the host and to not waste time to flash your device each time you will make any changes to your app. You probably know that flashing a device, it's rather a heavy task and it's time consuming. If you have a small app, for example, the Hello World one, it will be probably the few seconds, but once your app will become bigger and bigger, it will be a while to transfer your application to the device. And to avoid losing too much time for that, there is a desktop backend that provides you a way to test your things on the host machine. I also said that before, but just for convenience, I will repeat that. All needed Qt libraries that are for running desktop backend are delivered together with Qt for MCUs, so you don't have to install the big Qt and you don't have to have a license for it. MSVC compiler is used to compile desktop backend, so that's why Visual Studio is needed. But as I said, we are planning to provide MinWG compiler support, so then you don't need to have Visual Studio. All right, and we are slowly approaching the first live coding session, and let's see what you will learn during this live coding session. So for sure, you will see how to set up the CMake project from scratch. So from the empty file to some minimal subset of things that will allow you and enable you to build your app for Qt for MCUs. And of course, you will learn how to build that app using the command line. So with the most basic approach, and to run your app for both desktop and for the target. And so, well, let me set up things for you. Of course, we'll need some command line, and this is it. I will be using the commander, but it still can be a normal command line from the Windows. It's just a different terminal. You can use any that fits for you. And well, let's review the directory. So I have a special directory for this training. I will be keeping all of the files in this one. So just to have separate for our first application, I will create that. So mkdir first app. Let's go inside. Right now we will need some QML file to define our application UI. I will use Visual Studio Code for it. So just run code with main.qml and enter. Okay, here it is. So our empty file. Let's add something to define anything that we'll be able to identify. So for sure, import Qt quick. .15 and then rectangle. Let's give it some color. And it will be magenta. All right, I'm saving the file. And let's leave it as it is for now. And let's focus on providing CMake support. So once again, I'm getting back to terminal. And I will open a new file with a Visual Studio Code once more. And this time it will be CMake lists.txt. All right, and we have that one opened in the Visual Studio Code as well. Sorry, I need some water. I'm slowly losing my voice during all of those trainings. Regarding the CMake, we will need CMake minimum required version, minimum required version, and 3.15. We need to define the project for our application, and once again we will use the raw no-print project. Those two functions are the functions available directly from CMake, so this is nothing Qt for MCUs related yet. We are just setting up the things first. Up language is C++. And right now, let's start to use Qt4MCUs APIs from CMake. So we need the QL package, the Qt4MCUs package that will be visible for our CMake. And to do so, let's find package. And Qt4MCUs in CMake is called QL. All right. And right now we will start to use Qt4MCU specific CMake macros, and I will explain all of those one by one. So first one is to add the target. So this macro is covering the original target macro from CMake, and this provides a way to define the target, of course. And the most important thing that this macro is also supporting the kind of a way to compile your app to static library if you are going to link your application on some other last steps, some other more advanced steps of your product build process. But we are using the most simple way of it, so we are just passing the project here, and we are setting up the target. We need to add our QML file somehow to our project. So there is a special function for adding QML files, QL target. Just please no worry if you are not getting those CMake APIs. We will go through all of them in the later steps of the training. Right now it's just an example in live coding. QL target QML sources. First, and we have only main.qml. All right, and you can wonder because right now we are using just the main.qml file, and we are using the C++ language. So normally you will need the main function somewhere, and you can of course write that yourself, and you can run Qt4MCUs from there. But it comes with a default implementation as well. And if on the early steps of your application, you don't need anything specific in your custom, well, you don't need custom main function, then you can use one of the delivered together with Qt4MCUs. And to use that, then you just have to type up target default entry point, and you are going to use that for first up, and we have to tell which QML will be our root QML, and in our case it's a main, and you are just selecting it by selecting one of your QML files without extension. Right, and probably you can see that the first two macros were starting with QL, and the last one is starting with up, and that's not a mistake. All of the QL starting macros are the macros that are in general needed by our Qt4MCUs application CMake project, and those with up are just optional things, and that can be skipped, and then you can provide your own implementation for some things that those app macros are providing. In this case, it's, for example, the main function. So as I said, you can still remove that one and provide your own, but just to keep it simple, we are using the one that is already prepared. And let's save the file, and we are right now we'll try to build our application. Let's review what do we have there. So there are two files, main.qml and the CMake list.txt, and we are just about to build it. And before that, we need to set up the environment. And first thing will be to set some environment variables. And first one will be QL underscore dir. And let's point that to Qt for MCUs installation. So drive C, Qt MCUs, and the version. All right. We will need also some tools, and to use those, we need to add those tools, maybe directories with binaries of those tools to the path environment variable to make those visible for us. So set path, and please remember to preserve previous path content. All right. And we have to find CMake, and it's located in drive C, Qt tools, CMake, bin. All right. Let's verify. It works. Well, and that should be enough. Let's create a directory. Build desktop. Let's go inside. And right now, let's generate CMake targets for our desktop. So CMake, for the parent directory, we have to provide the platform, Qt platform, and platform for host is just a Qt, as it uses big Qt under the hood, so it's Qt. And let's select the architecture for it. And we have that generated. Let's try to build. So CMake, let's build this directory. So -- build this directory. So dot and then 2 dashes target first up, and then config to build release. And the build process has finished with success. So we can try to run our application. It's located in the release directory, and its name is just first app.exe. And as you can see, it does not work. And that's an expected thing. And as I said before, Qt for MCUs comes with the libraries that you need to run your application on the host machine. So right now, I'm just going to extend our path with a directory of the libraries that are needed there. So set path, it's the normal way of doing that on the Windows. I'm preserving the previous path, and I will use the qldir /bin. All right, and let's try to run it once again. And as you can see, we have exactly the thing we defined in QML files. So we have the rectangle of the magenta color. So we are able to compile and run our Qt for MCUs application directly on the host machine. And right now, let's focus on building that for the target board. So let's get back to the application directory, and let's create another build directory, but this time for the Renesas board. Make directory, build Renesas. Let's go inside. All right, and besides those environment variables that we already have defined, we will need some more to cover Renesas board, and this will be for sure the environment variable for compiler. This is ARM GCC dir, and it's also delivered together with Qt for MCUs installation, and it's located in the C, in my case in C drive Qt tools, Qt MCUs, ARM GCC 8. Okay, and we will need Ninja to use it with our CMake. So let's extend the path once again by preserving the previous content, and then Qt tools, Ninja. Let's verify Ninja. It works. Perfect. Well, the last thing to do is just to generate the targets. So CMake for the parent directory as previously. And there's the first difference, Qt platform won't be Qt anymore, and it will be EK-RA6M3G- bare metal to indicate which operating system or no operating system we'll be using. Then let's define the release build, CMake build type, release, and let's tell our CMake which compiler we will be using. So we will provide a toolchain file, which is also delivered together with Qt for MCUs, CMake toolchain file, you'll dir, and let's right now type that long path. So lib CMake you'll toolchain, and then ARM GCC .CMake. Last thing to pass Ninja as a generator. So let's try if that works. All right, so we have targets generated, and let's use Ninja to build our application. Ninja first up, and the build process is ongoing, as you can see. Linking process. And that's it. Some short summary of used data. And well, you can wonder how to transfer that application to the board. So Qt for MCUs comes by default with flash targets. It's done for each executable added to compile with Qt for MCUs, and it works by just well, it works that way. So you are just running CMake target that starts with flash underscore and then name of your application. And this will trigger internally the vendor tools to flash the device with just that one short single command. And right now I will show you what's currently on my device by just switching the presentation to content from secondary camera. So as you can see, this is my Renesas board, which is right now just showing the empty black rectangle. And we are going to flash our magenta rectangle to it. So right now I'm just starting the flash command. And that's it. Well, probably you cannot see the exact magenta color there, as the camera is, well, rather a low quality one. So, well, please trust me. This is a magenta color on the screen, but it's the flashing of the device. It's simple as this. So let's get back to sharing my screen, and just to show you how this looks like. So as you can see, Qt for MCUs flash target has used some JLink tool to connect to the device and flash the program to the board. All right. So this is about compiling your application in command line for both desktop and for the board. So this is the summary of it. Well, let's once again go through this. So you are creating this specific directory for your application, then you are setting some, of course, you're creating some files, QML files and the CMake list.txt. You are setting the environment variables, and the most important one, the QLDIR. You are generating the targets for your Qt4MCUs application by using a CMake, and you are building it with a default CMake style, or you can use generator for it, like we used Ninja for the board. Well, and that will be the only thing needed to compile and run your app. And do not forget to provide the directory with QLDIR binaries to let the operating system know where those missing libraries are located. And right now there is a time to go through rest of the QML, rest of the CMake APIs from Qt4MCUs. Some of them are those we have already used in the live coding session, but most likely the rest of them are something new for you. So still it could be an interesting part. So to configure your platform during the target generation, you are using Qt platform, of course, we use that. And for desktop platform, it's just a Qt, and it's the default one, so you can not provide that one, that thing for the host. And of course, it can be one of the boards that Qt4MCUs supports by default. Some Renesas boards, for example, RH850 or the one that I am using right now. Possibly the other vendors are also selected by modifying this variable. Qt color depth is used to define well, display color and to define the frame buffer format. So this should be one of the 8, 16, 24, or 32 values, as this defines the bits per pixel for our frame buffer, and by just lowering the value, you will allocate the less memory for the frame buffer, but you will also decrease the quality of it. And for the platforms that are using it with the layers, with the hardware graphical layers, this value means the default one. So you, for each layer, then you can define in the QML code a different color depth. QL@target is for adding, of course, executable target to CMake, and that comes together with some other features as well. So you can provide a static library optional argument to compile your application as a static library, and this could be especially useful if you are going to use your application as a library together with other components of your whole product. As we know that not in all cases you just can simply write the application, well, run the Qt4MCUs one. So if you are going to use it as a module in your whole product, it's still possible by using a static library argument. And the short example below that you are defining the target example app with two sources that are not the QML sources, but just the C++ source code or the C. To add the QML files, we are using Qt target QML sources. We also used that one in the first live coding session. So it takes the target, of course, for which one we are adding the files. Then there is a list of the QML files. And of course, we can pass some optional arguments like output directory to tell where the intermediate artifacts should be located. We can use the module URI, but this is the deprecated API that was an old way of creating QML modules. So you can still use it, but you shouldn't really. Copy QML files will mean that all the QML files that you provided in the list of the files will be copied to output directory as well. And that could be useful if you are building more complex solutions. Then some optional macros. So there is an app target default entry point, which follows the operating system that you have chosen and provides default main for your application. So if you are going to use the bare metal, it will be just a main function with initializing the root item that is based on one of your QML files, and then there is a short initialization of the QL that by just calling few functions, and finally you're running the endless loop with our rendering loop. And app target setup OS just well, setting up the things needed to run operating system. So if you are going to use FreeRTOS reference implementation, you'll probably need to run this macro to connect some initialization and the parts of Qt for MCUs that are normally not included there. This is to add the system-specific things. And the new way of doing the QML modules is to use add QML module, which will compile your QML files to separate static library. And well, let's go through the arguments. So of course, target URI to define the URI then used to import your module in other QML files. Of course, list of QML files, some headers for example, interfaces if there are any, some sources like C++ files, the imports that are used by your module, and of course, output directory for redirecting the artifacts from compilation. Ql add resource is for adding images. So this macro will be used for adding any PNG, JPEG, and so on files to your project. There are also a prefix and a base. So the prefix will mean that all of the assets paths will require prefix in your QML to access those files in the image component, for example. And the base path is to shorten the path of your files. For example, if you have in your project assets located in some, well, let's say complex and long directory, you can shorten that requirement of passing the whole path in your QML files by providing a general common base that will be added internally in our Qt for MCUs engine, and you will not have to provide that path in QML files. And of course, output directory to redirect all the artifacts to a different place. For translations, we have Qt target embed translations, which well, defines the translations and compiles in translation files in the binary form to your application. And to integrate your app with C++, you have the special macro to generate interfaces based on the C++ headers, and it takes the target, of course, the headers, and then the output directory, as always, to redirect the artifacts from the compilation process, well, and possibly the QML imports. Some APIs related to fonts. So Ql fonts dir will define where your fonts are located. Your custom fonts, by default, this value points to installation directory, source, third-party fonts, and there are default Déjà Vu Sans fonts delivered. And there's also a Ql default font family to avoid providing the custom font family for all text and static text components. You can define it globally to use it in all text and static text components with just one line. There is also the texture cache concept. So something that is used for various things, to be honest. So if you are going, for example, to keep your all of your images assets on the flash memory, but for some reason, for faster access, you will need to move them to the RAM memory during the runtime, they will end up in texture cache. And the same will go for the compressed images. So all compressed images normally are staying in the place that that you would like to stay them. And once they are decompressed, they are going to texture cache. And this is super important thing that if you are going to use that compressed images, you have to set the value of this variable, this cool texture cache, to at least size of the biggest decompressed image. So sorry, someone has connected to my Jabra, so I have to disconnect that one. I hope you still can hear me. Well, so as I said, you have to set this value to at least the biggest decompressed image. So size, width, and bits per pixel, plus the eventual padding of the alignment is the minimum size of your texture cache to fit at least one image, one biggest image in your texture cache. And setting it to the too low value can cause your application to stop working, and to big value can even cause a malfunction, as you can overlap other parts of your application, for example, heap or the stack memory regions, and that's probably not what you would like to do. Well, so just to remember that this is a really important API, but it has to be used with a special care to not make any problems. There are some additional CMake options to, for example, for debugging. So you can enable the bytecode by just defining cool debug bytecode, and this enables JavaScript bytecode generation, and then it will be generated as a comment to the right side of the artifacts files. And then there is also a cool debug line directives macro variable that allows you to enable generating the line directives that will point back to the QML source. And well, because all of the QML files are converted to the C++ during the compilation process, so your debugger will then know in which place in your QML file you should search for potential problems if you are debugging your application. Well, this was about the CMake APIs that are used to define your project, but right now I would like to focus on the overall build process that is a rather complex thing of the whole Qt for MCUs application. And let's focus on the left side, and I will go from top to the bottom by explaining all of the processes that are happening during the compilation process. So for sure, the input thing for whole compilation is the CMake list.txt file that defines your CMake project, defines your assets, fonts, and so on. So this is the definition of all of the things that will happen in the next steps. But well, let's be honest, all of the applications have assets, have fonts, have some logic behind this. So almost every application will follow all of the steps that are there. And the first thing in the compilation process is to compile your assets. So any PNG, JPEG, or any other images will go through the tool called QRCC. This tool is converting your PNG and other files to the formats that are known for Qt for MCUs. And normally, by default, all images are going to be a bitmaps on the Qt for MCUs side. And as an output, this tool produces the C++ files with normal row arrays of the bytes that are then interpreted as a particular format of the image. If you are going to use those images compressed, QL-RCC will do a recompression to the format and the compression known to Qt for MCUs, and then those arrays will be smaller things, but still some processing on those input files will be done to produce your artifacts and some intermediate code for application. The next step is to compile the fonts, and the tool QL font compiler is doing that. And what it exactly does, so it generates glyphs for your fonts. So if you are using some text elements, it will produce the glyphs for the letters and for the characters that you are actually using in your QML files. So it will produce only the range of the glyphs that is used in your app. Of course, you can extend that range, but this we will be talking later on. Well, and those glyphs will also be a bitmaps. This will be a different format. This will be alpha maps, so it will consume less memory than normal images. But still, it's important to know that the font compiler will produce the glyphs for each font type and size exclusively. So if you have the same font but different sizes in two different components, your glyphs will be generated twice. So you will consume the memory for the glyphs twice with different sizes. And it's also producing the artifact as in C++ file. After assets generation, so after converting the images, after generating the glyphs for fonts, there is a time to generate interfaces. For example, if you're going to connect your QML interface definition with C++ parts, so this is a part that takes care of it. So you have some input header files for your interfaces from the C++, and QL interface generator is converting those headers to QML representation to let the next tool know how to integrate your C++ logic together with the QML logic. So directly going to the next step and to compilation of the QML files, which means converting those to C++ implementation. And each QML file in Qt for MCUs is in fact converted to the C++ representation, and we are picking all QML files from your application and those from the previous step, and we are producing C++ representation of all of those. So if you are initializing any component like text, like your custom component, your, I don't know, rectangle, it will be converted to the C++ rectangle class, your C++ button class, and so on, and all of those things will be put into the C++ files, which are next artifacts for our whole compilation process. And finally, C++ compiler will take your own C++ files. Possibly this could be, of course, the C compiler as well, and will take all of the artifacts that are created during the compilation process, and will compile them all together and then link together with the libraries delivered with Qt for MCUs. And for sure, those will be at least QL Quick Ultralight and QL Platform Abstraction, and those two are the absolute minimum to run the Qt for MCUs application. But possibly you can use all other libraries for example, controls, PNG decoding, and so on. And after linking process, we have our binary ready. So this is quite a complex thing. So if you have any question to any part of this compilation process, please feel free to ask. I will try to answer that more clearly. But well, if any question will appear, I of course will answer this. But let me go to the next slide, which is about the QRCC itself. So this is about the tool that is to compile the images. As I said, it converts all of the images to C++ representation, to the bitmaps that are stored in the normal arrays. And this tool as well follows some desired resource loading policy. So if you are going to keep your file on flash or copy to RAM on the startup and well, whatnot, this tool will mark those arrays in the proper way to make sure that the platform will do exactly what's expected to do with those. It could also do some optimization for graphical transformation. It could mark some files that those will be transformed or rotated to gain some performance boost on this. It could compress the images if you are going to use those in compressed format. And well, the also important thing is that semi-transparent images can be optimized by this tool. And it's quite a great feature of Qt for MCUs. So for example, let's imagine you have the image that is that contains some borders or some accents for parts of your application, and most of that image is the completely empty space with fully transparent pixels. And this tool is able to split that image to separate parts of it, and then it can get rid of data that is well, just empty and not visible for the final user in the application. And by doing this, it can save really a lot of memory just for assets compilation. Well, yeah. So the next tool is Qt Font Compiler, and this tool generates glyphs that are also stored in the byte arrays as pre-rendered alpha maps. I also said that it defines and generates glyphs for each font size combination. So more fonts and more sizes, different sizes of the fonts in your app will mean more glyphs generated and more memory consumed for those. And glyphs are automatically selected and generated for text that is in your QML files. And as I said, it can be overridden by defining the ranges of additional glyphs you are supposed to use in your application. So it's completely fine to provide additional set of the glyphs that you're expecting to use in your app. Well, yeah, that's it about this tool. And to generate QML interfaces to your C++ classes, you will use QML interface generator tool that converts your headers to QML representation, which is then used by other tools to properly understand what is the logic behind this and how to connect those things together. And this tool forwards the properties, signals, and the functions from your class to the QML. So this will mean you will be able to use the normal C++ function and run it from the QML code. And that's a pretty good feature. And the same goes for the members of the class that could be properties of or the signals. And the QML to CPP, it's the tool to convert the QML files to C++ representation. And it's done for each QML file. It also defines how to initialize those components on the C++ side. But well, it's completely transparent for you. It's something that is done, well, it's hidden, but it's important to know how it works. And this is about the first part of our training. And right now there is a time for a short coffee break. So if you have any questions to the parts that we covered during the first steps, well, then please ask. And if not, I will just start the timer for you to make sure that we have the same hour everywhere. All right, I don't see any questions, so I'm starting the timer, and let's see each other in 15 minutes. A bit more rest right now. So with the batteries